Good morning, everyone. My name is A. Avinash. I am explaining about reducing operation on sequence aggregative values. In the real computer science and algorithm optimization, reducing operations on sequence aggregate values is crucial technique for improving efficiency and performance. This approach focuses on minimizing the number of computations required when dealing with the large datasets or sequences of values that require aggregation. By employing clever mathematical properties and data structures, we can significantly reduce the time complexity of operations on this sequence. This not only speeds up calculation but also allows for more scalable solutions to complex problems. Throughout this presentation, we will explore various techniques, their applications, and solve example problems to demonstrate the power of reducing operations on sequence aggregative values. Introduction to sequence aggregative values. Sequence aggregative values are the result of applying an operation across a sequence of numbers or data points. These operations typically combine elements in a specific order to produce a single output value. Common examples included sums, products, and maximum values and the average of the sequence. First one definition. Sequence aggregate values are derived from applying an operation across a sequence of elements, resulting in a single output. And there are the properties is these operations often have associated and cumulative properties, allowing for flexible computation order and applications is sequence aggregative values are used in various fields, including statistics, data analysis, and algorithm design optimization potential. The nature of these operations allows for various optimization techniques to reduce computational complexity. Motivation for reducing operation. The primary motivation for reducing operation on sequence aggregative values stems from the need for efficient algorithms and optimized performance, especially when dealing with a large datasets or real-time applications. As data volumes continue to grow exponentially, traditional methods of computation can become prohibitively slow and resource intensive. First one, improve time complexity. Reducing operations can significantly decrease the time required to process large sequences, often transforming algorithms from O of n r words to O of log n or even O of one time complexity. And the second one is resource optimization. By minimizing the number of computations, we can reduce CPU usage and energy consumption, leading to more efficient and environmentally friendly solutions. Third one is scalability. Optimized algorithms can handle larger datasets and more complex problems, enabling the development of more powerful applications and systems. Fourth one is real-time processing. Reduced operations allow for faster processing of streaming data, enabling real-time analytics and responsive user interfaces in time-sensitive applications. Common sequence aggregative functions. Sequence aggregative functions are fundamental operations that combine elements of a sequence to produce a single result. These functions are widely used in various fields of computer science and mathematics, forming the basis for many algorithms and data processing techniques. Here are some function description and example order. First one is sum. Add all elements in a sequence. Product is multiple all elements in a sequence, and maximum find the largest element in a sequence. Minimum find the smallest element in a sequence, and average calculate the mean of a sequence. In the first one sum, we will add the all number of elements and we will write that answer, and the product we will multiply with each of the element, and the maximum we will find out the largest element in the list. Minimum is we will find the smallest element in the sequence, and the average we will calculate the mean of the sequence. Techniques for reducing operations. To effectively reduce operations on sequence aggregative values, various techniques have been developed by computer scientists and mathematicians. These methods leverage mathematical properties clever data structure, and algorithm insights to minimize computational complexity. Mathematical properties. Utilizing associative and cumulative properties of operations to reorder computations for efficiency. For example, there is a plus b plus c plus d can be computed as a plus d plus b plus c if it leads to faster evaluation. Pre-computation. Calculating and storing intermediate results to avoid redundant computations. This includes techniques like dynamic programming and memorization. Data structures. Employing specialized data structure such as segment trees or sparse tables to efficiently store and query aggregated values over different range of a sequence. Prefix sums or partial sums. Prefix sums are also known as partial sums are a powerful technique for reducing operations on sequence aggregative values. Particularly for sum-based queries, this method involves pre-computing cumulative sums of a sequence, allowing for constant time range sum queries. First, pre-computation. Pre-computation. Calculate the prefix sum array where each element is the sum of all previous elements in the original array. And next, second, storage. Store the prefix sum array which has the same length as the original array. Third one is query. To find the sum of a range I comma j, simply subtract prefix from prefix of j. Update. For dynamic arrays, update all subsequent elements in the prefix sum array when modifying the original array. Difference arrays. Arrays are also known as discrete derivative arrays or technique used to optimize range update operations on sequences. This method is particularly used when dealing with the multiple range updates followed by point query. Construction. Create a difference array where difference of I equal to array of I minus array of I minus 1 with difference of 0 equal to array of 0. This represents the changes between adjacent elements in the original array. Range update. To update a range, L, R by value V, simply add V to difference of I and subtract V from the difference of R plus 1. This operation takes go of one time regardless of the range size. Reconstruction. To obtain the final array after updates, compute the prefix sum of the difference array. Each element in the result represents the cumulative effect of all updates. Point query. To query the value at index I, compute the prefix sum of the difference array up to index I. This gives the final value after all updates. Optimizing lookups. Optimizing lookup is crucial for efficient querying of sequence aggregative values. Various data structures and techniques can be employed to achieve faster lookup times, especially for range queries on large datasets, segment trees. Hierarchical structure allowing for efficient range queries and updates in uh, Ingo of log n time, ideal for dynamic sequences with frequent updates and queries. Second is pen trees, also known as binary indexed trees. This provide a time complexity bingo of log n updates and queries for cumulative frequency tables. Excellent for scenarios with many updates and prefix sum queries. Sparse tables. Precomputed table for faster range queries on static arrays offers bingo of one query time with bingo of n log n recursion. Suitable for immutable sequence with frequent queries. Hash tables provide bingo of one average case lookup time for point queries. Useful for scenarios where fast individual elements access is required. Examples, problems, and solutions. To illustrate the power of reading operations on sequence aggregative values, let's explore some common problems and their optimized solutions using the techniques we have discussed. First one, range sum queries. The problem is given an array of integers. Efficiently answer the multiple queries for the sum of elements in a given range, L, R. The solution is use prefix sum to precompute cumulative sums enabling bingo of one-time range sum queries. Second one is range update point query. The sum is perform multiple range updates, add a value to all elements in a range, and answer point queries efficiently. For this question, we have solution is implement a difference array to handle range updates in bingo of one time and reconstruct the values for point queries. Third one, sliding window maximum. We have a problem that find the maximum value in every continuous subarray of size k in an array. So, solution is use a DQ to maintain potential maximum values, achieving window of n time complexity for entire operation. And the fourth one is 2D range sum queries. The problem is given 2D matrix, efficiently compute the sum of elements in a rectangular region. Solution is implemented 2D prefix sum matrix, allowing for bingo of one times query for any rectangular region. Reducing operations in practice. Applying techniques to reduce operations on sequence aggregative values can significantly impact real-world applications. From database systems to final analysis tools, these optimizations play a crucial role in enhancing performance and scalability. First one is database optimization. Implementing efficient indexing structures and query optimization techniques based on sequence aggregative value reduction can dramatically improve database performance, especially for large-scale systems and handling millions of transactions. Financial analysis. In high-frequency trading and real-time financial analysis, reduced operations enable faster processing of market data, allowing for quick decision-making and more accurate predictions. Network monitoring. Efficient algorithms for processing sequence aggregative values are crucial in a network monitoring tools, allowing for real-time analysis of vast amounts of traffic data and quick detection of anomalies or security threats. Thanks.